Hello and welcome everyone. My name is Rick Frage. I'm the sales director at SF Tech. Today we have a very informative webinar. It's not a very long one. It's not very technical either. But we're going to discuss the ICC certifications, the ESR and the EER reports, their importance in the industry and how they would help GFRP being accepted in the industry. So before I start, I'd like to welcome everyone who joined today. Thank you very much from all over the world. I see a lot of different people from different regions. So let's get started. I would like to start by introducing the two experts that are presenting today. So at the beginning, we have both Dr. Girish Narayan, Prajapati, and Ahmed Al-Badi. Both are PhD from University of Sherbrooke, and they are working with us as expert engineers in the GFRP field. So let's start with Dr. Girish, since he's the one who is going to start the presentation. So Girish basically has PhD, as I just mentioned, in civil engineering from the University of Sherbrooke in Quebec, Canada, and Masters of Technology in Earthquake Engineering from Indian Institute of Technology. He received the University Gold Medal in 2013 for Bachelor's of Technology project on strengthening of reinforced concrete columns with externally bonded fiber reinforced polymer from Veer Surendra Sai University of Technology in Burla, India. So basically, as you can see, he's an expert in also not only GFRP, but also GFRP in seismic zones, and concrete structures in seismic zones in general. His research interest at the University of Sherbrooke mainly includes the behavior of structural concrete reinforced with fiber reinforced polymers, testing and characterizations of FRP materials, and nonlinear finite element analysis of reinforced concrete structures. Girish is a senior structural researcher at SF Tech. He's been with us for about a year and a half, I would say, give or take, which we are based in Montreal, Quebec, as most of you know. He's a MyTax postdoctoral fellow at the University of Sherbrooke in Canada. He assisted us during his work with us in several different projects, from helping to convert steel structures into FRP, like reinforced with steel into reinforced with FRP, for different types of projects and structural elements. He designed things for us from scratch as well, from retaining walls to structural slabs to vertical walls and all these things. Now about Dr. Ahmed, you might be surprised there's a lot of similarities. They both got their degree from University of Sherbrooke. However, Dr. Ahmed did his Master's of Technology in Construction Engineering from the Helwan University in Cairo, Egypt. He also received the University Gold Medal, first ranking basically, in 2010 and for Bachelor of Civil Engineering from the Faculty of Mataria, Egypt. His research interest includes the behavior of structural concrete reinforced with fiber reinforced polymers, testing and characterization of FRP materials, tunneling reinforced with FRP bars and FRC, and nonlinear finite element analysis of reinforced concrete structures. Both engineers have very similar experiences. One specializes a little bit, Dr. Girish specializes a little bit more in the seismic behavior of structures, while Dr. Ahmed is more specialized in the tunneling, and that differentiates them a little bit. Dr. Ahmed also is a senior structural researcher in SF Tech. Again, he's been working with us for about a year to a year and a half. And a MyTax postdoctoral fellow at the University of Sherbrooke as well. Again, Dr. Ahmed helped us a lot with similar projects from shear walls, structural slabs, vertical applications, and all these things. He also contributed in the revision of the reports for the EER reports before submitting them to the ICC for review. I'll leave the mic for Dr. Girish, and then afterwards he will pass the mic to Dr. Ahmed to continue. Girish, the mic is yours.
Yeah, thank you, Rick. Thank you, Rick, for the brief introduction, and good afternoon, everyone. So today's topic is the important topic because we are going to talk about how FRP certification work and a guide to the ICC-ES EER-5081. So the whole presentation is divided into two parts. So the first part, I will be presenting the first part on the SFT-Bar certification. And before starting our main presentation, so let's look at the SFTech and their products and what service we offer. So our products are mostly designed in Canada and are manufactured in China by Sandog Safety Industry Co. Limited. So who are specialized in manufacturing of fiber reinforced polymer products. So we work with national and international engineering firms. We work with them through the design process and help them with the fiber reinforced polymer design standard, whether they are in Canada or in the United States. So we focus on parking facilities, water treatment plants, retaining walls. So our focus is mainly on the glass fiber reinforced polymer bars. So the SFTech FRP bar is made from composite materials like fiberglass, and it is manufactured by a pultrusion process using a mix of recycled fiber and resin. And the following figure shows a microscopic view of the FRP bar. So there are basically four types of fiber used in the fiber reinforced polymer bars: glass, fiberglass, carbon, basalt, and emerald. So glass is the widely available nowadays, and it is used in most of the projects in North America. So we can produce different types of FRP products depending on the project requirements. And some of the FRP bars we produce are straight bars, spiral, stirrups for transverse reinforcement, bent bar, and glass fiber reinforced polymer shear connectors. So this glass fiber reinforced polymer bar is widely used due to the production cost and have better tensile strength compared to the other types of FRP bars. So some of the advantages of the aseptic glass fiber reinforced polymer bar are it have longer service life because of its corrosion resistance. So therefore, improved durability in harsh environments such as construction near the coastal area in Northern American cold climates. So the FRP bar have better resistance against corrosion compared to the steel bar. And the tensile strength of FRP bar are around 2 to 3 times more than that of the steel bar, the normally used steel bar. However, it have more tensile strength. FRP bars are lighter due to the low density compared to the steel bar. Their density is around 1/4 of the density of the steel. And due to the corrosion resistance, FRP bar are good for the harsh chemical environment as well. And it is neutral to the electric and magnetic disturbance, useful for the applications such as in airport, military application, or MRI rooms in hospitals. So some of the selected field application of the SFTech FRP bar we have already done in Canada are GFRP bar, reinforced concrete waffle flooring slab designed with SFTech glass fiber reinforced polymer bar. And this was built in Halifax, Nova Scotia. And it can also be used on slab on grades or slab on grounds. It is a non-structural slab. It is a one-to-one replacement and saved a lot of money compared to the steel bar in terms of labor and transportation. So another project, so the cast on-site precast sandwich panels, and they have used our glass fiber reinforced polymer bar in their project as the reinforcement. And in the right is a retaining wall built for the city of Montreal. And the retaining wall is designed to dump snow with de-icing salt during the winter. So they built this retaining wall with aseptic glass fiber reinforced polymer bar, and which provide resistance against the chemical used in the de-icing salts. So coming to the first part of the webinar on aseptic bar certification. So the ICC-ES ESR-5081 certificate, it evaluates the aseptic bar, and the scope of the evaluation are compliant with the 2021 and 2018 International Building and International Residential Code. So according to the evaluation report, the aseptic bar is used as tension reinforcement, such as in flexural concrete member, beams, shallow foundation, one-way or two-way slabs. It can also be used in as vertical reinforcement in concrete columns and walls. So the the SFT-Bar can also be used when engineering design is submitted in accordance with the IRC section R301.1.3, and it is approved by the building official in accordance with the IRC section R104.11. ICC uses acceptance criteria 454 for the fiber reinforced polymer bar for internal reinforcement of concrete structures, and the scope of the test program was determined following the requirements given within the table 1.2 of ICC AC 454, and it determined the physical, mechanical, and durability properties. And the test requires for the all these physical, mechanical, durability properties are presented in the following slides. So starting with the physical properties, so 4 different kinds of physical properties are required for the certification. Those are cross-sectional area, fiber mass content, moisture absorption, and the glass transition temperature. So the glass fiber reinforced polymer used in the current certification were produced according to the filtration process and were made of continuous glass fiber embedded in vinyl ester resin matrix. So all the GFRP bar in the study had a helical wrap surface to increase the bond between the bar and the concrete. The 4 different types of GFRP bar were investigated: number 3, number 4, number 5, and number 6, which have a nominal diameter ranging from 9.5 millimeter to 19.1 millimeter. So the volumetric method is used to measure the cross-sectional area due to the external surface coating of the GFRP bar doesn't allow to calculate an adequate cross-sectional area. The specimen were tested in accordance with the ASTM D7205 and ASTM D792. So the ASTM D792 is used to compute the specific gravity or density of the specimen. The instrument used in the test were cylinder and measuring scale. The specimen were baked with an analytical balance to 1 milligram precision. So 8 samples from each production lot were tested. So total number of lots were 3 lots, and total number of samples will be around 24. So each fiber reinforced polymer specimen was weighed with an analytical balance to a 1 milligram precision, and its length carefully measured with a measuring scale. And then the specimen were placed in a graduated cylinder filled with water and weighed. Finally, the cylinder was filled with water and weighed. The cross-sectional area of the specific surface in the square millimeter, it was calculated using the second equation where D is the density of the specimen and 0.998 is the density of the water at room temperature. And MS is the mass of the specimen, MW is the mass of the water in the cylinder, MSW is the mass of the water and specimen in the cylinder, and L is the length of the specimen. So for the tested helical wrap glass fiber reinforced polymer bars, the averaged measured cross-sectional area was greater than the nominal cross-sectional area as shown in this table. And it was in between the required cross-sectional area according to the AC 454 acceptance criteria, which has been made based in the table number 3 of the ASTM D7957. So the AC 454 acceptance criteria suggest that the requirements should be met according to the ASTM D7957. In the second test, the fiber content of the GFRP bars was measured, and it is an important parameter that determines its mechanical properties. The specimen were cut to 1 inch for fiber mass content and was tested in accordance with ASTM D2584. The instrument used in the test were muffle furnace capable of maintaining at least 600 degrees Celsius temperature, a desiccator to cool the specimen. The specimen were weighed with an analytical balance. The 1 inch FRP samples were heated at 565 degrees Celsius until the carbonaceous material disappear and the remaining residue is cooled and weighed. The fiber content by weight percent was calculated using the following equation where the W1 is the weight of the specimen and W2 is the weight of the residue. And for the tested glass fiber reinforced polymer bar or the SFT-Bar, the average fiber content was found to be higher than 70%, which is required in the ASTM D7957. So the moisture absorption is an important test, and it's aimed to prevent excessive moisture absorb that can weaken the bar. And the importance of moisture absorption test is that how we can know what kind of resin is used in our bar, like we are using vinyl ester or polyester resin in our bar. So it is an important test to distinguish the type of resin matrix. The FRP specimen were tested in accordance with the water absorption procedure 7.4 in ASTM D570. And the instrument used in the test were drying oven capable of maintaining the required 50 degrees Celsius. A water container was used for the absorption. The specimen were weighed with an analytical balance. The specimen were initially dried in an oven for 24 hours and weighed after cooling it in a desiccator. So this weight was called a condition weight. And after conditioning, the specimen were placed in distilled water, which was kept at 50 degrees Celsius. The first weighing occurred after the 24 hours, and then again the specimen were immersed in the water. Then again we extracted it and weighed it every week until we reached the saturation level. So the saturation was confirmed when the increase in the weight over the 3 consecutive measurement was less than 1%. The water absorption at 24 hour and 2 saturation was calculated as increase in weight in percentage equal to the weight minus the condition weight divided by the condition weight. For the helical wrap glass fiber reinforced polymer bars, the average measured water absorption at 24 hour and 2 saturation was lower than the requirement values in the ASTM D7957, as we can see from this figure. So for 24-hour limit, it is around 0.25%, and we get very, very less value. And for at saturation, the limit is 1%, and the value is below 0.4%. The aseptic bar specimen were tested in accordance to the ASTM E1356 to find the glass transition temperature. So the instrument used in the test were differential scanning clarometer was used with aluminum pans. The specimen were also weighed here, and small size specimen were cut and placed in the heat chamber, which was kept under a nitrogen flow during the scanning procedure. So a heating ratio of around 20 degrees Celsius per minute was applied. And the value of the glass transition temperature was taken at the mid height of the phase transition as shown in this figure. And for the aseptic GFRP bar, the average measured glass transition temperature was greater than the 100 degrees Celsius requirement in ASTM D7957. Now coming to the mechanical properties, which includes tensile properties, transverse shear strength, and bond strength through pull-out test. So the tensile properties, or we can say the longitudinal tensile properties of FRP specimen were tested in accordance with the D7205, and the instrument used in this test were Baldwin testing machine and an extensometer for displacement recording. The test specimen was prepared by installation of steel tube on the both side of the FRP sample using expensive cement, and the length of the steel tube was around 40 times the diameter of the bar. The specimen was instrumented with a 200 millimeter extensometer to capture the specimen elongation during the test, and this test was carried out using the Baldwin testing machine. The tensile load was applied until the failure occurred, and the applied load and the bar elongation were electronically recorded using a data acquisition system. And the tensile strength of the FRP bar can be calculated according to the following equation, where Fu is the tensile load in Newton and A is the cross-sectional area of the tested bar in square millimeter. The tensile modulus was calculated by a fitting by fitting a straight line to the data using the method of linear least square regression analysis. The strain range selected for the fitting line was within the lower half of the stress strain curve, with the starting point at a strain of 1000 microstrain and end point being the 6000 microstrain. For the helical wrap glass fiber reinforced polymer bars, the guaranteed tensile properties were greater than the requirement in the ASTM D7957. And here the guaranteed properties means the mean tensile load minus 3 times the standard deviation. The transverse shear strength of FRP specimen were tested in accordance with the ASTM D7617. And the test apparatus consists of two bar seat, two lower blades, and two guide machines from steel. These parts are bolted together with two threaded ruts and washer and nuts as shown. And the upper plate is loose and is fit into the bar prior to the testing. So the length of each specimen, irrespective of the bar size, was 225 millimeter or 9 inches. And the specimen was centered within the shear apparatus, resting against the bar seats and lower blades. And we placed the upper plate into the place into the bar and centered the apparatus in the MTS universal testing machine. So the displacement rate was selected so that the product should fail within 1 to 10 minutes, and force was applied uniformly without subjecting the specimen to impact. So after testing the samples in the shear up to failure, the transverse shear strength was calculated using this equation, where P is the failure load in Newton and A is the FRP bar area in square millimeter. For the SFTech GFRP bar, the average transverse shear strength were greater than the 131 megapascal requirement in the ASTM D7957. So coming to the last test, last mechanical property test, which is the pull-out test, were performed to measure the bond strength between the reinforcing bar and the concrete. The test apparatus consists of bonding testing machine, loading plate, LVDT at fixed and free end to measure the displacement, concrete mold, and steel tube. So here ASTM D7957 allow bond test on either odd or even bar size designation if a range of identical produced bar is offered. So therefore, the pull-out test was were conducted on GFRP bar number 3 and 5, which are the odd bar size. The GFRP bar were embedded in the concrete blocks after applying the steel pipe anchor to one end of the bar as shown in this figure. And the free length of the GFRP bar between the block and the anchor was approximately equal to 40 times the diameter of the bar. And all the test specimens were prepared using one concrete base, having a target compressive strength of 35 megapascal. So a debonding PVC pipe was attached to GFRP bar to prevent any transmissions of the force by the bond between the bar and the concrete to ensure testing length of 5 times the diameter of the GFRP bar. So a displacement control test was conducted at the rate of 20 kilonewton per minute using the universal testing machine. And the GFRP bar slippage was monitored using one linear variable displacement transducer. And the applied load and the bar slippage were recorded automatically throughout the test with a computerized data acquisition system. So all the bar failed in pull-out failure with no cracks observed at the concrete blocked surface after the failure. So the bond stress at the peak load was calculated assuming a uniform bond stress distribution along the embedded length of the GFRP bar in concrete, and that is along the length equal to 5 times the nominal diameter of the GFRP bar. And for the SFTech bar, the average bond strength was above the requirement. The requirement is around 7.6 megapascal as per ASTM D757, and both number 3 and number 5 exceeded this requirement. So the only durability or aging property required on the SFTech bar for certification was the alkaline resistance without any applied sustained load and the alkaline resistance of the SFT-bar was determined post-accelerated aging exposure immersed in a high pH solution without any applied sustained load as per ASTM D7705. The instrument used in the test were Baldwin machine and extensometer for displacement recording and a chamber to maintain 60 degrees Celsius temperature. So once it was exposed in a high pH solution, then the testing process which followed was according to the ASTM D7205, which is for the tensile properties of the FRP bar. So here also the ASTM D7957 allow alkaline resistance on either odd or even bar. So therefore the alkaline resistance test was conducted on GFRP bar number 3 and 5 only. So the test specimen was prepared, similar preparation as we did for the tensile properties after the exposure. So we installed the steel tube on the both side of the FRP sample using expensive cement. The specimen was then instrumented with 200 millimeter extensometer to capture the specimen elongation during the test. And the test was carried out using the Baldwin testing machine, post-accelerated aging in a high pH solution. And it was in the exposure for 3 months, at least for 3 months at 60 degrees Celsius. The tensile load was applied until the failure occurred, and the applied load and the bar elongation were electronically recorded using a data acquisition system. So the experimental tests presented for the mean alkaline resistance based on the mean tensile load are summarized in this table. And we saw that the AC454 acceptance criteria has been met based on the table 1 of the ASTM D7957 specification, and it should be equal to or more than 80% of the mean tensile load of the without exposed GFRP bars. So the aseptic bar must be designed in accordance with the ACI 440.1122 and Chapter 19 of the International Building Code. The aseptic bar is used in tension reinforcement such as flexural concrete members, beam slabs, or foundations, and vertical reinforcement in concrete columns and walls. So the bond-dependent coefficient, it's account for the degree of bond between the FRP bar and surrounding concrete in ACI design standard, and it should be taken as 1.2 for aseptic bar, which is as per the ACI 440.11. The analysis of the flexural capacity must be based on a strain compatibility approach, which is similar to the steel reinforcing bars. The reinforcement details, minimum concrete cover, and the installation should comply with the provisions of the ACI 440.5. And if you are using the aseptic bar, it should be stored above surface of the ground on platform or other support as close as possible to the point of placement. And if you are storing the aseptic bar outdoors, so it must be covered with opaque plastic or other types of cover that will protect the bar from the ultraviolet rays. So coming to the next presentation, so it will be presented by Dr. Albedi.
Thank you, Grish. Thank you, Rick. Now I will take you through the second part of our presentation, focusing on a guide to EER-5081. In this segment, we will cover the evaluation of EER-5081, its applications, the reasons why EER-5081 is a virtual choice for engineers, and conclude that with a practical design examples. What is EER-5081 certification? It is an equivalency evaluation report that certifies our safety bars for specific applications. It is issued at March and revised at June 2024 and renewal every year. It should be mentioned that the calculations and results of respective EER tables are based on ICC ESR 5081. This certification is guaranteed by the ICC evaluation service, ensuring that our products meet the required standards and are approved for use in designated projects, including the construction of single-family houses, double or duplexes houses, and buildings of 3 or more townhouse units. limited to 3 stories above grade plan. In EER-5081, the evaluation and performance of structural elements, including concrete foundations, walls, and lintels, when reinforced with SFT-Bar GFRP bars, are comprehensively reported. What sizes of SFT GFRP bars are used in ICC EER-5081 applications? 3 bar sizes of number 3, number 4, and number 5 were used to reinforce the applications in EER-5081. All bars are characterized based on the AC 454 acceptance criteria of the ICC. It should be noted that the properties of SFT bar are presented in ESR-5081 as my colleague Girish presented earlier. Additionally, the evaluation in EER followed the 2021 and 2018 International Residential Code, IRC. Specifically, specifications are 403, 404, 506, and 608. In this slide, there are some conditions to use EER as follows. The ICC Equivalency Evaluation Report addresses only conformance with the noted IRC sections. This report applies only the design parameters submitted for review by ICC-ES. For insulated concrete forms, ICF walls, when used, it must comply with the IRC requirements or have an ICC-ES evaluation report. The design criteria in this report or in this certification: risk category 2, 2 stories above grade, and seismic load A and B, while seismic category C is for basement wall only. Let's explore the benefits for engineers, consultants, and distributors when using our EER certification. Ease of design: it simplifies the design process for structural elements, including concrete walls, lintels, and foundations. Safety assurance: our report ensures that the designs comply with the ACI 440 code and its requirements. It should be noted that compared to same certification with other available GFRP bars in the market, we have increased the safety factors to ensure a safer design. Global usage: the EER certificate can be used for designs in Canada, the USA, and worldwide, providing trustworthy tables for building design. Finally, this report is introduced by our expert engineers and top consultant design office, ensuring a high reliability and quality. EER-5081 comprises tables and drawing details. For tables, wall designs above grade are reported in tables 2, 6, and 7. Walls designed below grade are reported in tables 1 and 5, and tables 3 and 4 show the designs of lintels. For drawing details 1 through 4 show plan diagrams and section details for walls and foundations. How can engineers use EER perspective tables in design easily? Firstly, for design walls, number 1, determine the type of wall, above grade or basement wall. Number 2, choose concrete strengths from 2,500 to 4,000 PSI. Number 3, determine the location of bars centered or placed at 2-inch with concrete cover. Number 4, determine wall height from 7 to 10 feet. Number 5, determine backfill height from 4 to 9 feet. Number 6, determine the lateral soil load, 30, 45, or 60 pounds per square feet. Number 7, choose the wall thickness from 6, 8, 10, 12 inch. And finally, choose safety bars, bar number 3 or number 4 or number 5, and each spacing. Finally, draw details based on the EER sections. Secondly, how can engineers easily employ EER tables in lintel designs? For lintels with load bearing, number 1, determine wall thickness determine lintel depths, choose load conditions from 1 through 5 as per table R608.8, determine the snow load 30 or 70 pound per square feet, and finally, using SFT GFRP bar of size 4, get the spacing. Conversely, when designing lintels for non-load bearing purposes, number 1, determine lintel depths from 8 to 24 inch, determine wall thickness from 4 to 10 inch. Number 3, choose the lintel supporting from light framed gable or concrete wall. Finally, using SFT GFRP bar of size number 4, get the spacing. The following slides present a design example of a typical plan diagram. In the shown plan, we will focus on designing one wall, as shown in this slide. The design criteria as follows, and it's required to design wall reinforced with SFT GFRP bars based on EER-5081 certification, and the other solution with ICF wall reinforced with steel bars based on ICF-MA tables. Finally, make a comparison between GFRP and steel reinforcement, both vertically and horizontally. The design data provided in EER-5081 and ICF-MA tables are shown in this slide. It should be noted that the bars in both solution with 2-inch concrete cover. Beginning with the solution of RC wall using SFT GFRP bars based on EER-5081, we will first outline the steps for analysis and design. Choose number 1, basement wall. Choose the concrete strength, 2,500 PSI. Choose 2-inch concrete cover in number 3. In step 4, choose the wall height, 8 feet. Number 5, choose the backfill height in step number 5 as 7 feet. In step 6, choose 45 BSF for design lateral soil load. In step 7, choose wall thickness of 6 inch. Finally, based on table 1 of the EER-5081 certification, we will utilize the SFT GFRP bar number 5 with a spacing of 28 inches as vertical reinforcement in the RC wall. For horizontal reinforcement, we will follow the guidelines provided in the footnotes of the EER report. This entails placing one number 3 bar within 12 inches of the top of the wall and one number 3 bar near the mid height as specified in table R404.1.2. To design the same selected wall using an ICF wall reinforced with steel bars based on ICF-MA tables, we will follow the specifications provided. Number 1, wall height, backfill height, the lateral soil load, the wall thickness, and finally using steel bar M15 at 18 inch as in table B11 in vertical direction, and horizontally we will use steel bar 10M at 16 inch. This slide shows a comparison between steel and SFT GFRP bars. The table demonstrates that RC walls reinforced with SFT GFRP bars based on EER-5081 is considered the most economical solution beside other benefits of using GFRP bars as in corrosion resistance along the surface life. Finally, the conclusions can be listed as follows. There is a strong case for use of FRP bars in structural concrete exposed to corrosive environment. Using EER-5081 for designing GFRP reinforced walls is considered a safe and reliable solution. GFRP reinforced walls with SFT GFRP bars using EER certifications, ESR and EER-5081 are a more economical solution than ICF walls with steel bars. Finally, engineers, consultants, and distributors can use our EER-5081 easily with more benefits. All products, certifications, data sheets are available on our website and can be downloaded easily. Thank you for your attention.
Thank you, Dr. Ahmed and Dr. Girish. I personally would like to add a couple of things that I guess from a sales perspective are important. First, going back to the ESR report, which is the part where Dr. Girish explained, I would like to highlight that most of our competitors has ESR reports for one or two sizes only. So it can be a little bit confusing. It's always double check their certificates. If you're designing with, let's say, number 5, which is 15 millimeter, make sure they have the ICC-ESR for number 5, not just for number 3 or 4, which most of the competitors have for 3 and 4 only. A lot of them also have tested for non-structural applications. They do not, the ICC-ESR having the certificate does not necessarily mean that you can use the bar for structure. It just means that it passes certain specs, mechanical specs that it has been tested for. Doesn't mean that it has been tested for everything. That makes it reliable for structural elements. One last thing regarding the ESR report again is that our bars exhibit. If you pull out all the ESR reports that are published on the ICC website today, you will notice that SFT-Bar exhibits the highest specifications among all of the competitors. Some of them actually there's a big difference as well. So it's not us when we tell you we are at least one of the top bars in the market. We're not saying this because it's our bar. We're saying this because of the ICC certificate that came out and proved what our claims based. Now going back to what Dr. Ahmed's part of the presentation, the EER report. Also from sales perspective, there's only one competitor that has the EER report. You will notice because of the difference in specifications between us and the competitor, our spacing is slightly larger than their spacing. So basically using our bars will save you a little bit more. On top of that, we know for a fact that our bars are more competitive in price, one-to-one comparison. Also, the EER report in a lot of municipalities, especially the smaller ones, has been accepted across a lot of municipalities across the US. So basically what I mean by accepted, it means that they're accepted as an equivalent design to steel bars or steel bars tables that are in the IRC code. So there's, in some cases, they do not require extra engineering. So it's a good plus for resellers or for contractors actually doing these types of works. It saves a little bit of money, especially talking, by the way, on residential applications. This is the IRC code. It's not commercial. So I just wanted to add these comments.